Good day, everyone, and we meet yet again. And today we're going to discuss voltage versus current graphs. This is under Ohm's law, and I just wanted to make sure that you understand how to interpret these graphs, but not only that, to also be able to answer the relevant questions when it comes to that. So, if you haven't subscribed, please make sure that you do the right thing. Please subscribe to our channel. And by the way, you are more than welcome to just put a thumbs up if you like this lesson. And please just throw a good comment whilst you are at it, so that we can continue to produce these great lessons for you. All right, so today I want to look at voltage versus current graph. Okay, so in this case, what we normally have, we have a setup. So suppose that we have a setup of a circuit, just like this one. So what we normally do is we put a rheostat. Okay, a rheostat is basically a variable resistor. You know, it's a resistance whose resistance rather, you can vary, you can change it. Okay, I want you to think of a stove. You know, normally you've got a knob there that turns between 1 and 6 for some of them. Okay, so that's a variable resistance. Okay, you vary how much heat you want, so you just switch on, just turn on that knob to the level that you want. Okay, that's basically a variable resistor. So when we have this setup, what we want to find out is we're basically running an experiment where we want to determine the internal resistance of a circuit, right? So essentially we want to find out about the EMF and the internal resistance. And so what we do is we'll connect the ammeter, obviously in series, to our rheostat. We will also connect a voltmeter just across our resistor. And what we want to measure is we want to keep measuring the voltage across this resistor against the current. So perhaps, let's say at the beginning, we'll set our resistor at, suppose, let's say 10 ohms. Okay, so at 10 ohms, I know the amount of current that would flow, right? I would measure the voltage across that, and I would also measure the current that passes through that emitter there. But then I switch the knob again, and I say, let's say our resistance is now 20 ohms, right? So now what's going to happen? It's going to decrease the value of my current over there, but in this case, it's also going to decrease the reading of the voltmeter there, right? So in essence, I just wanted to draw a typical graph that you'd probably get from that particular circuit. So I'm going to do this the first way, right? So normally you would get a graph that has to be voltage on the one hand and current on the other. Okay, so I would have voltage over there. Okay, and in this case I would have current. Okay, so you get a graph that would typically look like that. So I'm taking a voltage versus current graph. All right, now you would end up with a graph that more or less looks something like this, and I'm going to explain that to you just now. Okay, right, so meaning that as the current keeps increasing, right, the voltage value is going to decrease, if you note that. Right, so why exactly do you get this kind of a graph? Now I want you to remember we had an equation whereby we were looking at EMF is equals to V external, okay, plus V loss. All right. If you haven't watched our previous videos on circuits, please do so, so that you can understand what we are doing now. Right, so we basically broke this down and said, okay, but we know what V external is. It's I total, it's the total current that is passing through a circuit, okay, multiplied by, so it's I total multiplied by R external. So that would be the resistance of this this rheostat. Okay, so okay, and V loss, what is that? It's the current across our internal resistor, right? So it would be I total multiplied by the internal resistor. So in essence, this is the kind of equation that you have, and this is where we derived now the equation that we normally use. I, that's the common factor, and I isolate that, that's R external plus the internal resistance. Okay, so that's where we get that E is equals to I R, but remember, which R do we use? We use the external resistance as well as the internal resistance in that case. Okay, right, so let's start here. So when is the current 0? Okay, so when I open this switch here, remember there's no current that's flowing in our external circuit. In fact, you know what, I think it would actually make more sense if I were to put this voltmeter over there. It would actually read the same thing, right? So if I were to measure the voltage across our battery here, now note, if the switch is open, there's no current that is going to move across our circuit. Now please, I want you to note this carefully. The moment there is no current in our circuit, the voltage reading over here will be the reading of the EMF. Why? Because in that case, note that you will not have V loss. Remember that V loss, okay, which is the voltage across our internal resistance. You can call it V internal if you want to, okay? So the moment we don't have current, all right, remember it's going to be 0 multiplied by R, and in this case it means that your V loss value will be equal to 0. And so as a result, if V loss is 0, then E is equals to V external, right? So it means that the V external value will actually be equal to the EMF. So in these circuits, they always, or well, they have a way of somewhat asking you to write down the value of the EMF. Where are you going to get the value of the EMF? You'll just check where your current is 0, right? This voltage reading over there is basically your EMF value. Okay, so I'm going to conclude this video with an example, by the way, so just stick around. If you don't understand as I explain, it's fine, but as I do the question, it will be much clearer. Okay, right, so now, so it means that what now begins to happen is that when I now close the switch and there's current that is flowing, all of a sudden there's a V loss, there's voltage that is lost, right? And that voltage is lost due to the external resistance, right? To the internal resistance rather. Okay, so what happens? This voltage reading over here now begins to drop, right? So it means now V loss is significant, there's a value there. So EMF, remember, it stays the same, it's designed within the battery, right? So in this case, the external voltage decreases because now some of the energy is actually lost due to the internal resistance. So as a result, the more that you keep increasing current, okay, the greater our V loss value, and as a result, our V external value keeps decreasing, okay? And that's what gives this trend that you have over there, okay? So in fact, there are two things that I want you to note. So the EMF value, but also it means that we can also determine. Now I want you to please note, if I were to have points there on my graph, okay, right, now I can calculate the value of the internal resistance. And how do I do that? You simply get the internal resistance by simply taking the gradient on our graph. So whenever you've got a graph like this in circuits, then you know that the gradient here must give you the value of your internal resistance, okay? So how do we calculate the gradient? Remember, it's going to be the change in Y divided by the change in X, but what's our Y in this case? It's the change in voltage divided by the change in the amount of current. Okay, now remember that in this case, voltage divided by current. Okay, if you remember Ohm's law, right? So V is equals to I times R, right? Okay, I don't know why I made that so small. Okay, let's write it over here. Okay, so we've got V is equals to I multiplied by R. So if I want to get resistance, it's always going to be voltage divided by current. Okay, so in actual fact, so when I calculate the gradient underneath this graph, okay, of course you're going to say V2 minus V1. You must always be careful to say divided by I2, so the current value must be taken from your initial voltage value, right? Minus I1. So remember, in this case, all we're simply saying is that your EMF value will be on the where current is 0. So you might find some instances where they just flip this around, where they have current on the y-axis and voltage on the x-axis. Just remember, in that case, you'll need to invert it, right? So all that we're simply saying is that the change in the voltage divided by the change in current will give us our internal resistance value. Okay, and then we know that our EMF will be where the current in this case gives us 0. So what I want to do is, let's take a past exam question and let me illustrate this point to you. And by the way, I'll be also skilling you on how to read off from graphs. Okay, shall we go? So I took this question from Gauteng 2019 prelim. Okay, so they gave us a graph like this. Okay, I'm just going to try and zoom in when we do the question. So they say a group of learners conduct an experiment to determine the EMF and internal resistance of a battery, right? They say the data obtained from the experiment is used to plot the points on the graph on graph paper and draw the line of best fit, right? So they say the graph of one of the learners is given below, and the x and y axes have not been labeled. Okay, now if you note there, okay, I would strongly, okay, believe that the y-axis in this case would represent the voltage, okay, as well as the x-axis would represent the current. All right, even though that's not written there, right? So now the first thing that they ask us to do is to explain the term internal resistance. So by definition, we say that internal resistance, you shouldn't really stress too much about this definition. It's really quite an easy to understand definition. So we say the resistance, the internal resistance rather, is the resistance within a battery that causes a drop in the potential difference of the battery when there is a current in the circuit, right? So it's the resistance that causes a voltage drop, right? It causes the voltage to drop when there is a current in the circuit. Now, I want you to please note, in this case now, what I want us to do is to focus on the questions that follows. They say write down one factor which must be kept constant during this experiment. Of course, in this case, we must always make sure that temperature remains constant. Okay, right, now let's go into the graph. They say using the graph, now we need to provide a label for the y-axis. As I did say to you, you can do that yourself. Okay, that would be voltage there and this would be current over there, and it makes sense. Those current values kind of make sense. Okay, so you'd have voltage against current. And then they say write down the quantity represented by the gradient. You see. So that's what we said previously. We said the gradient in this case represents it represents the internal resistance, isn't it? So we know that the gradient represents internal resistance. And look at what they deliberately do. They say write down the EMF of the battery. So that's the part. I want to just get this drawing to be somewhat closer so that you all can see it. Okay, so I'm just going to zoom in a little bit on it so that you can see it there. All right, so now let's take the values as we see them on this circuit. So we want to find out what the EMF is. Remember, we said the EMF, where do you get the value of the EMF? When the current is 0. So we said these values here represent current. This is where current is 0. So now we need to go and read off from the graph. And that's the skill I said I want to make sure by the end of this video you are able to master. Okay? So if we look at that graph there, you'll see that the divisions, okay, so you've got 0 to 2.0. So the major lines kind of show you the scale, okay. They are measured in terms of they have a scale of 2, right? But now note that you've got the smaller lines in between. So those minor lines in this case, you'll always, well, most of the time you'll see that if you count them, there's about 10 of them, okay? So if you say, okay, I'm going to do that here. If I say, I'm going to, now I want to find out the scale. It's going to be 2 minus 0, which is that 2 minus that 0 over there, right? Divided by how many lines do I have in between? I've got 10. So actually I get 0.2, right? So it means they increment or they increase, all right, one to each other by 0.2. Okay, so you'll see that if I start at 0, for instance, and I take the smaller line, okay, so it's 0.2, 0.4, 0.6, 0.8, 1. Okay, so 1 at line number 5, that would be 1 there. Okay, right. Now if I take that same thinking and I now go where there is my EMF value, which is right over there. So it starts from 6. Remember, I increase by 0.2 for each line, right? So that will be 0.2. So that's 6.2, 6.4, 6.6, 6.8, 7. I think I get that value to be 7.2. Yeah, I get it to be 7.2. So my EMF value, remember where the current is 0, okay, that's my EMF value. So I get that value to be 7.2. I hope that you understand that. We said the current, okay, the EMF will be we'll take the EMF where the current is 0. So I get a value of 7.2. So I can write that down and say, well, it means that E for the circuit is going to be 7.2 volts. Okay, I'm going to zoom out just a little bit so that you can see the rest of what I'm writing. Okay, so that's 7.2. And then now look at what they said. They didn't say calculate the EMF. They said write it down. So they expect you to find it somewhere. Okay, now let's take the next question. They say calculate the internal resistance of the battery. Right, now this is the part that I want you to see. So how would I get the internal resistance? I'd say, well, the internal resistance would be my gradient on this graph. Now note that my gradient is going to be change in voltage divided by change in current. So change in Y over change in X. All right, something quite specific I want you to see there. So let's take V2 minus V1 divided by I2 minus I1. Okay, so now what I'm simply going to do there is I'm going to make sure that I take two values from my graph. So I don't want to make things complicated for myself. Okay, you can choose, by the way, any two values along your graph. All right, so what I'm going to do is, let me rather pick the values at my intercepts, meaning I'm going to take my where y is 0, where x is 0 rather, and where y is 0. By the way, there's nothing stopping you from taking any of those values in between. Okay, it's just that obviously it would require a bit more work. It would be a little bit more tedious, right? So let me take that as my V2 value. So that would be my V2 and I2. Remember, you start with the X, so I'd start with the I value. So there it would be 0, okay, and 7.2. You remember that? Okay, so that's my current value, my voltage value over there. So this would be 0 and 7.2. Okay, so I know the value there, 0. This is where I is 0 and voltage is 7.2. And then I go to this one over here. Okay, when I look at it, it seems as though my current is 0.8. Okay, and my voltage would be 0 over there. Okay, so remember, it's the X and then the Y. So my Y is 0 over here and my X is 0.8, right? And then over there, my current is 0 and my voltage is 7.2. Okay, so let's call that I2 and V2, and let's call that I1 and V1. Okay, so let's calculate there. So my V2 value, this would be 0 minus my V1 value is 7.2 divided by, right, we start with I2 again. So in this case, I2 is 0.8 and my I1 value is 0. Okay, right, let's get that calculation going. Okay, I get a value of 9 ohms. Okay, that's minus 9 ohms. Of course, you're going to get that value as a negative. So remember, please don't be unfazed. Don't be fazed by that negative there. Okay, that's absolutely normal, because in this case we are measuring a decrease in the voltage. Okay, so it means that the value, our internal resistance in this particular case, therefore our internal resistance will actually be equal to 9 ohms. Okay, remember that resistance is a scalar quantity, right? So in that particular case, that is how we would measure the voltage, the internal resistance. But perhaps what I need to do, let me just show you. You could have taken any of the other values, by the way, just to calculate that internal resistance. Right, I'm gonna try. Okay, I know this, I'm getting myself in trouble here. So I'm going to try and label maybe any of the other points in that graph over there. Okay, so let's try to find another point. In fact, let me do this so that I don't mess it up. Let's take perhaps that value there. I seem to get, let's see. So this would be, so that's 0.4 and 0.6. Those are major lines. Remember, there's 10 of them. So that's 0.2 divided by 10. So that's 0.02. So in this case, I would have 0.4, let's say. So that value here would be 0.6 minus 0.02, so that would be 0.58. Okay, so my current value would be 0.58. Okay, and my voltage value would be 2 over there. Okay, I know you can't see that quite clearly. All right, so my current value here would be 0.58, and my resistance, my voltage value will be 2. Okay, so I could have taken that value there, right? And you can take, let's say we take that value there. Okay, so I see over there I've got 0.4 over there, So that would be 1 2. So this would be 0.4 minus 0.02. That would be 0.38, 0.36. So this value here would be 0.36. And what would be my voltage value? My voltage value is 4. I'm just trying to show you that you could have picked any of the values there and still calculate that internal resistance. Okay, so now I'm going to repeat the same thing. So R is equals to change in voltage divided by change in current. Okay, so I'm going to say V2 minus V1 over I2 minus I1. Okay, so let's do that. So remember, that's my current, that's my voltage. So let's take that as our V2 value. I'm going to say that's 4 minus 2 divided by, okay, so I started with this value, so for my current I need to start there again, 0.36, okay, minus 0.58. Okay, let's put that in our calculator and see how close a value it will be to that which we found. Okay, and I get a value of 9.09. Okay, so let's say minus 9.09. Okay, ohms. Can you see they're incredibly close to each other? So in that case, of course, it wouldn't be the exact same value, obviously, because you are running an experiment over here, and this is the line of best fit, so it's not exactly a straight line graph. Okay, so in that case, that is how you'd calculate your resistance. Just a word of caution, ladies and gents. Okay, sometimes it is possible for them to give you the same graph, but in this case you would have voltage over this side, current over this side and voltage there, right? So when you have that situation where they give you a graph of current against voltage, let me just try to illustrate that to you. So they say, well, this would be current here and this would be voltage over there. You'd still get a similar shape of a graph. Okay, but now just a word of caution. Remember that when you calculate your gradient, now let me just call it M. So it means that your value of M is now going to be the change in current divided by the change in voltage. Okay, so if you think about your Ohm's law, okay, we said V is equals to I times R, right? So you'll see that resistance is voltage over current, but this time you've got current over voltage. So you no longer have your internal resistance, but what do you have? You've got the inverse of your resistance. Okay, so that means you will calculate the gradient, and upon, let's say you got you found a gradient to be minus 0.3. I'm just making an example, right? So say you found your gradient to be minus 0.3. What you then need to do to get your internal resistance, you'll say the resistance would be 1 divided by that 0.3 there, and in this case it would give you say 3.3, whatever that value will be. Okay, right? So remember that once you've got current against voltage, then it means that you just need to go through that extra step of finding, in this particular case, the inverse of the gradient, and then determine that as your resistance. So remember, you get a negative value, but remember that your resistance is actually a scalar quantity. So in that case, you would keep it as positive. I hope that makes sense, ladies and gents. Okay, now as I conclude the last part of this question, they say determine the value of the internal voltage, right, when the graph reaches 0.8. So they want to know what would be the internal voltage over there. Okay, so that would be quite simple, right? Because Because what happens actually at that value, okay, where the current is 0.8, you'll see that the V external is now 0, okay? So meaning if the V external is 0, now let's take the equation again, where we say E is equals to V external plus V loss, okay? Right, and you'll see why that is equal to 1 mark. So in this case, what do we note? We see that our V external now has decreased to the point where it has become 0. Remember, when we increased the current, V external, this value now gave us V external, right? But when we keep increasing the current until we get to the point where V external is 0, so therefore it would mean that V loss or V internal, as they call it here, would now, if this value is 0, right, then it means that your V loss would now be equal to the EMF value. So we can just simply confidently say our internal voltage there should be equal to that value that we got there, which is 7.2. The value that we got over there, which is 7.2. Okay, so just remember at this point here, we said here we get the EMF, all right? But here, this is the value where we are going to we are going to get V internal equals to our EMF value. Okay, so I hope that made sense. Otherwise, ladies and gents, I want to keep it here. Please, if you haven't subscribed, please make sure that you do the right thing. And I will see you again next time. In the next episode, I think I want to just tackle also graphs that have to do with resistance. So look out for that. Okay, see you again next time, ladies and gents. Sharp, sharp.